The last type of trigonometric equation we are going to learn how to solve is a trigonometric equation when the argument is not exactly theta. So let's read here. It says the input to a given trigonometric function is called its argument. If the argument is not exactly theta, it may instead be a multiple of theta, okay, meaning that your argument is going to look like this, k times theta, where k is a real number. So examples include what you see in a double angle formula as well as a half angle formula. You might see the cosine of 2 times theta. 2 times theta is your argument, so it's not exactly theta, it's double theta. And then you might have a half angle formula, like I said, so your argument would be theta over 2, which is again not exactly theta. Any multiple angle would work here, so you could also see something like the cosine of 5 times theta. Again, your argument is close to theta, but not exactly theta. It's been multiplied by something or it's been divided by something. The other way you can have an argument that's not exactly theta is if a horizontal shift is present. So what your argument is going to look like in that case, it will be theta plus or minus some number. So an example of this type of argument is right here, where you have the cosine of theta minus pi over 2. Okay, the entire quantity you're taking the cosine of here, theta minus pi over 2, is your argument. So your argument is not just theta, it's more complicated. Okay, so we're going to talk about how you would handle an equation where your argument is more complicated than theta. So it says to solve a trigonometric equation when the argument is not exactly theta, there's two things you can do. Either one, you're going to use a known identity to make a trigonometric substitution. We've done that method before with another type of equation. Or you're going to do the following. Okay, and this may sound a little confusing, but we'll do an example and hopefully it will make sense. You're going to replace each instance of the argument in the equation with u. Then you're going to solve the resulting equation for u over an interval whose length equals the period of the function. Then you're going to add multiples of the period to the solutions found in step 2, replace u with the original argument, and then finally solve each equation from step 3 for theta. Okay, that's confusing. It will make more sense when we actually do it, but the whole gist of it is a u substitution. Okay, so you saw me doing that with the quadratic equations, like when we were factoring, and then the sine of x or the sine of theta made it confusing, so we called the sine of theta u, and then we replaced the sine of theta with u, and then worked the equation with u, and then went back to thetas. Okay, so it's a similar kind of thing. All right, so when we see an argument that's more complicated than theta, we are either going to do the u substitution thing, or we're going to use a known identity to make a trigonometric substitution. Okay, so let's take a look at page 10, okay, where we have example 9, and it says solve the equation over the interval 0 to 2 pi, and also for all solutions. The equation is 2 times the cosine of x over 2 minus the square root of 2 is equal to theta, or sorry, is equal to 0. So when you look at this, okay, x is what you're actually solving for. Okay, you're not solving for x over 2, you're solving for x. Okay, so this is a half angle. Okay, you've got x over 2. It's a half angle. Okay, so your first thought might be, well, I know all those half angle formulas. Okay, well, you remember how absolutely crazy those half angle formulas were. Okay, those were the messy, messy, messy ones. So we're not going to go that route where we make a trigonometric substitution. This would be a good one. The half angle ones are a really good idea to use the u substitution on. Okay, so I'm going to take my argument, that's what I'm taking the cosine of. I'm going to let u be x over 2. Okay, and then I'm going to go to my original equation. Everywhere I see x over 2, I'm going to put a u. So this is going to be 2 times the cosine of u minus the square root of 2 is equal to 0. Okay, so now we kind of forget about the x's. The equation's been turned into u's. we're going to solve for u. Okay, so this is linear. Okay, we've got one trig equation, which is cosine, and it's raised to the first power. So we're going to isolate the cosine of u. We want to get it by itself. Okay, so we're going to add the square root of 2 to both sides. This tells us that 2 times the cosine of u is equal to the square root of 2. Now to get the cosine of u by itself, we have to divide off the 2. So I'm going to get that the cosine of u is equal to square root of 2 over 2. Okay? All right. I am going to go to my unit circle and try to solve this. Okay? So I am trying to solve the cosine of u is equal to the square root of 2 over 2. Okay? We know cosine is associated with the x value. We know that the cosine here is positive, and we know that cosine is positive in quadrants 1 and 4, so that's where we need to be looking. Okay, so what angle has an x coordinate of square root of 2 over 2? Well, right here, so pi over 4. And then if we look in quadrant 4, 7 pi over 4 is also going to work. Okay, so those are the two angles we are looking for. These are angles, these are values of u, okay? Because I am solving the equation cosine of u is equal to the square root of 2 over 2. So u can be pi over 4, or u can be 7 pi over 4, okay? If you put x here, that's wrong, okay? It has to be a u value, okay? So if I go back to my work here, u can be pi over 4, or it can be 7 pi over 4, okay? We are not done. You can't go straight to this box and write those down as the solutions between 0 and 2 pi, because again, those are the values of u. When you are solving this original equation, you're looking for the x value. So at this point, you have to go back and replace what u is. U is the same thing as x over 2. Okay, now here's something else major that you have to remember. Okay, remember we're going to have to not only write the solutions between 0 and 2 pi, but we're also going to have to write down all solutions. Okay, so before you do the substitution here, you need to go ahead and start formatting the all solutions part. Okay, so I'm going to come up here and I'm going to write that u can be pi over 4. I'm going to do these separately, so I'll make another statement for 7 pi over 4. I am going to go ahead and add integer multiples of the period. Okay? You have to do it at this point, or it's not going to come out correct. Okay? The all solutions part won't. Okay? So, like I said, cosine, its period is 2 pi. Okay? So I'm taking the pi over 4, and then I'm adding integer multiples of the period, and I have to do it right now while it's still a u. Okay, and then I'm going to do the same thing for the 7 pi over 4. Take it and add integer multiples of the period. Okay, then I'm going to go ahead and replace it. Okay, I know that u is the same thing as x over 2. Well, let me keep it in blue. All right, so this is going to be x over 2 is equal to pi over 4 plus 2 pi times n. Okay, and then this guy would be x over 2 is equal to 7 pi over 4 plus 2 pi n. Okay, now the equation has been converted back to x. That's what we want. We want x values. Okay, x, how do you solve for it? Well, it's being divided by 2. So you need to multiply by 2. If you do it to one side of the equation, you need to do it to the other side, okay, on both of these, okay? So what am I going to get? Okay, on the left side, 2 times x over 2 is going to give me x, okay? And then you need to distribute the 2 through the right side of the equation. So we're going to get for this first equation that x is going to be 2 pi over 4 plus 4 pi n. Okay, so if you simplify this, this is going to be pi over 2 plus 4 pi n. Okay, so here is one of the general or all solutions statements. Okay, And then we need to do the same thing for this bottom one. We need to distribute here. So this is going to be x equals, if we distribute the 2, we're going to get 14 pi over 4 plus 4 pi n. Okay, if you simplify this, 14 and 4 are both divisible by 2, so you're going to get 7 pi over 2 plus 4 pi n. So this is the other statement for all solutions. Okay, so I'm going to go down to the box and write these statements in. So my general solutions are all solutions. Okay, my first statement is going to be, well, let me change the color. X is going to be pi over 2 plus 4 pi n. Okay, and then the other statement is going to be x can be 7 pi over 2 plus 4 pi n. Okay, and again, this is where n is any integer. Okay, now we need the specific solutions between 0 and 2 pi. Okay, so if you go back, you may say, hey, pi over 4 and pi over 4 and 7 pi over 4, I'm done. Those were u values, not x values. Okay, so what we can do here is use our general statements to generate the solutions between 0 and 2 pi. Okay, so I'm going to start with the first statement here. I'm going to plug in, and I'm talking about the pi over 2 plus 4 pi n. Okay, if I plug in x equals 0, okay, or sorry, if I plug in n equals 0, that's going to tell me that x is equal to pi over 2 plus 4 pi times 0. This goes away, so pi over 2. Okay, so that's a solution. Okay, that works. And then if I plug in n equals 1, okay, so that's going to give me that x can be pi over 2 plus 4 pi. Okay, well, just by the nature of adding 4 pi to it, okay, this is going to be outside of 2 pi. Okay, so that's going to be bigger than 2 pi. Okay, so I'm not going to write that one down. Okay, if I had looked on the other side of n equals 0, if I did n equals -1, the same thing would happen here. If I put in -1, okay, I would be taking pi over 2 and subtracting 4 pi. So this is going to be less than 0. Okay, so that's not going to be a valid solution in between 0 and 2 pi. Okay, these are solutions, but they're not between 0 and 2 pi. Okay, you need to check the other equation. Okay, so if we take the other equation and we pop in n equals 0, we're going to get that the x value is 7 pi over 2 plus 4 pi times 0. That's going to be 7 pi over 2. And that is actually bigger than 2 pi because this is 3.5 times pi. Okay, so this is bigger than 2 pi, so we don't want to include that one in our solutions between 0 and 2 pi. And then if I look at, well, we can't go bigger, then we can't do n equals 1 because that's going to be way too big. If we did n equals -1, let's see what that would give us. 7 pi over 2 plus 4 pi times -1. So this would be 7 pi over 2 minus 4 pi. So that's minus 8 pi over 2. That's 4 pi. That would be negative pi over 2. Okay, negative pi over 2 is a solution, but it's not between 0 and 2 pi, so we're not going to write it in the box. Okay, so by plugging in various n values, we realize that based on our general solutions, the only solution between 0 and 2 pi is pi over 2. All right, so that's it. We are done. We've got both the specific solution between 0 and 2 pi. We've got the general solution statements. What I really need you to take away from this example, if you are doing a u substitution like this, when you're doing the general solutions, you absolutely have to write your general statements before you convert the u back to x. Okay, if you don't do that, you're going to add on the wrong quantity, and then the remaining solutions are going to be incorrect.